In this video series so far, we always used a laser pointer as the light source, which has nearly parallel light beam. Now we will show you the effect of non-parallel light source. Nevertheless, we want to keep the laser pointer because we still need to use monochromatic and coherent light source to show the diffraction pattern. Those needs can be fulfilled by placing a convex lens in front of the laser pointer. We can add another lenses to achieve higher solid angle of the light beam, hence larger spotlight on the wall. Before the lens, the light beam is still approximately parallel. After the lens but before the focal point, the light beam is converging, while after that it becomes diverging. Right at the focal point, the light beam is mostly affected by spherical aberration of the lens. First, we put a single-edged obstacle before the lens, where the light beam is still approximately parallel. The result is a shadow cast on the wall with slightly blurry edge. Note that the shadow is on the opposite direction from the obstacle, since the lens reverses the light beam. Now we put the obstacle after the lens, where the light beam is no longer parallel. Near the lens, which is before the focal point, the shadow is reversed. Right at the focal point, it is hard to tell whether the shadow is reversed or not, and it looks blurred. Even slight movement of the obstacle can change the shadow dramatically. After the focal point, the shadow is not reversed anymore. Let's take a look closer to the shadow from the experiment just now. The bright spot is produced by the diverging laser beam. Some pattern that you see is caused by irregularities of the lenses. Now let's put the obstacle in front of the lens before the focal point. The obstacle is actually coming from the left, but the shadow is reversed, thus comes from the right side. We can find light and dark bands on the bright area which is not covered by the obstacle. We also see that the shadow of the obstacle doesn't have well-defined edge. It seems that some part of the light beam can go through it. Let's move the obstacle as close as possible to the focal point. Now slight movement of the obstacle can change the shadow dramatically. The light and dark band formed as interference pattern is wider than before. Now the obstacle is moved further from the lens to a place beyond the focal point. The shadow is no longer reversed, but the pattern is similar to when the obstacle is before the focal point. Now we'll use a thin wire as the obstacle and repeat the experiment. Near the lens, which is before the focal point, the shadow of the wire is seen on the wall, accompanied by dark and bright bands beside it as a result of interference pattern. At the focal point, the diameter of the light beam is so small, even smaller than the width of the wire. Hence, the shadow is cast over entire light spot. The wire also widely spread the light beam well beyond the width of the light spot. Further away from the focal point, the shadow of the wire on the wall is back again. Again, let's take a look closer to the shadow from the experiment just now. First, we put the wire near the lens prior to the focal point. We can see the shadow of the wire on the wall, but we can also see a bright line in the middle of the wire's shadow. There are also dark and bright lines beside the shadow. Now when the wire is moved closer to the focal point, the shadow gets bigger. At the focal point, the shadow is bigger than the spotlight, and the whole spotlight becomes dimmer. Note that at this point, the light beam is very small, hence it is hard to keep holding the wire on it by hand. We can also find the light beam is widely spread beyond the spotlight. When the wire is moved further away from the lens, the shadow as well as fringe beside it shrink again. Finally, when the wire gets closer to the wall, the shadow looks like normal shadow without apparent diffraction nor interference pattern. Next, we use triple wire aperture to repeat the previous experiment. Let's take a look at the shadow closer. Next, we are going to do the experiment using diffraction gratings. First, we use 100 lines per millimeter grating. We can see the spotlight is split into many bright spots on the wall. Note that their size don't seem to change much as we move the grating closer to the wall, while the distances among them gets smaller. Note also that, unlike previous experiment, the spotlights on the wall don't seem to change much as the grating moves past the focal point of the lens. Similar features are also observed with 300 lines per millimeter grating, although it produces fewer bright spots and separated further away from each other. With 600 lines per millimeter grating, we get even fewer bright spots on the wall.